Good morning all. Greetings. This is the lecture 10. In this lecture, I'm going to cover determination of heat and work transfer for closed systems under different process. So in earlier class, I have covered the first law of thermodynamics, that is Joule's experiment. After then, how to conduct the Joule's experiment, what is the experimental setup, and finally what are the conclusions that it could be brought out. Next one is it has covered the corollaries of a first law of thermodynamics. So reminding the corollaries of a first law of thermodynamics, that is internal energy is a property of a system. Second one is internal energy energy of a system remains constant. Third one is perpetual motion machine of the first kind. So that particular contents it is covered in the lecture 9. Now today I am going to cover first law of a thermodynamics applied to the different process. That is once after obtaining the relation Q is equal to delta E plus W from the first law of a thermodynamics, now you need to apply that Q is equal to delta E plus W to the various process. So here today's topic is Q is equal to delta E plus W, and that delta E plus W applied to the various non-flow process. So in the second part, it is applied for the flow work, right? So for today's class, today's class going to cover the non-flow work and its heat transfer relations. So here the objective of this particular course is already it is covered so many times, but once again reminding the content, imparting the knowledge of a thermodynamics to know the student how the heat and work interactions are taking from the system with the surroundings. With respect to that one, what are the heat transfer and work transfer relations when a system is undergoing the different process? So that is what for today's class. And here the outcome, develop the heat and work transfer relations, for various thermodynamic process in closed system using the first law of thermodynamics. Now, in this case, it is going to cover the cyclic and non-cyclic process. So already I told you that the work can be classified as a non-flow work, and another one is the flow work. So the non-flow work is nothing but you can call it as a piston displacement. So in the earlier class it is already covered, piston displacement work. Right? So that is nothing but the PDV work. Right? So this is the non-flow. That is what it is covered in the earlier class. So now, the thermodynamic process can be precisely categorized as the cyclic process and the non-cyclic process. cyclic process and the non-cyclic process. So what is the cyclic process? A process is the one, cyclic process is the one in which the initial and final states are identical. That is, system returns to its initial state after the occurrence of a process. System returns to its initial state after the occurrence of a process. So here, if you draw the PV plane, that is this is system 1. That is, system 1 changes from state 1 to the state 2 following the path A, and this is B. So this is nothing but a cyclic process. This is nothing but the cyclic process. Cyclic process. So non-cyclic process. The non-cyclic process is the one in which the initial and final states are different. That is, the occurrence of a process is accompanied by the state change. Occurrence of a process is identified by the state change. So that is nothing but the non-cyclic process. Cyclic process and non-cyclic process. Now, going to cover the energy balance equation for a closed system. Energy balance equation for a closed system. So the meaning of this one is how you are going to represent the energy equation in a first law of thermodynamics in various forms. In various forms. So that is the energy balance for a system undergoing any kind of a process. Observe whether it is a constant pressure process or constant volume or isothermal or adiabatic or polytropic. So the first and foremost thing what you have to write is that is what is the amount of energy entering, energy in, and what is the amount of energy leaving. What is the amount of energy leaving. So finally, what is the total energy content in the system, right? So the net energy transfer by heat or work and mass. This is a change in internal kinetic energy, potential energy, chemical energy, nuclear energy. So like that one, this is the total change, that is delta E of the system. Delta E of the system. Whereas in the rate form, that means with respect to the time. So with respect to the time, where you have to represent as that is energy entering in with respect to the time, that is E dot minus E out with respect to the time, that is equal to change in energy by dt, dE by dt. So rate of change. So that's why here rate means when we call it as a rate, then the time is going to be appearing, right? So E dot in, E dot out is equal to dE by dt. Rate of change in internal energy, kinetic energy, potential energy, all kinds of energy. All kinds of energies. So this is the change in energy of a system. Change in energy of a system. So observe the units here. This is kilojoule and this is kilojoule per second. Kilojoule per second, that is nothing but equal to watts. Right? Clear? So that is the difference between that is the representation of the energy balance for a closed system in any process, and strictly in a rate form, how you are going to represent the thing. Next one is Next one is for constant rates. For constant rates, the total quantities during the time interval t, total quantities of energy during the time interval t are related to the quantities per unit time. Quantities per unit time means small e is equal to capital E by time, right? So that is small e here. Small e is nothing but equal to capital E by m. That is the energy balance. This can be expressed on a unit mass basis. That is E dot in, E dot out is equal to delta E of the system. That this is what small e is equal to capital E by m. That is why this is in kilojoule per second. So this is the closed system. This is the cyclic process. For a cycle, right? For a cycle, E is equal to 0, Q is equal to W, right? So that is the sigma of a Q is equal to sigma of a W, right? So for a closed system undergoing a cycle, the initial and final states are identical. For a closed system, when it undergoes a cycle, the initial and final states are identical, and thus delta E of the system, delta E of the system. So this is the delta E of the system, that is in this one, of the system is equal to 0. That is the E2 minus E1 is equal to 0. Then the energy balance for a cycle simplifies to E in minus E out is equal to 0. So always most that is here what you need to remember is that what is the energy in and what is the energy out, and this is the delta E, right? So E in minus E out is equal to 0, right? So noting that for a closed system, this does not involve any mass flow rate. So because we are discussing the non-flow work, that is control mass technique. Closed system does not involve mass flow across its boundaries. So for a closed system, only the energy interactions are taking place. Mass is not transferred across the boundaries. The energy balance for a cycle, this can be expressed in terms of heat and work interactions are. So that is W net is what is the W net is going to be come out when a network is when a net heat input supply is given, right? So what is the Q heat input is given and what is the work output which is expected from the system. So this is what the energy balance equation for a closed system. Energy balance equation for a closed system, and the representation will be like this particular way you have to represent. So this is the general energy balance, that is Q minus W is equal to delta E. For a stationary system, this delta E is nothing but it is the microscopic and macroscopic energies. But for a stationary system, the microscopic energies are considered. Q minus W is equal to delta U. Only the microscopic energy for a stationary system. And per unit mass, where Q minus W is equal to delta E. So always, for this small q, that is capital Q by mass. So that is this one, small q, work input and change in energy. In a differential form, this is expressed as d bar q minus d bar w is equal to de, right? D bar, that is d bar q or d bar q minus d bar w is equal to de. This is the differential form. So the energy balance for the first law relations is already given or intuitive in nature. It are connected to the natural process and are easy to use when magnitudes and directions of heat transfer are known. So you can easily apply the first law of thermodynamics to the natural cases. However, when performing a general analytical study or solving a problem that involves unknown heat, sometimes we may be knowing the heat or sometimes we may be knowing the work, right? So one has to be found because the first law of thermodynamics is nothing but conversion of one form of energy to the another form. So what is the one form of energy entering and what is the another form of energy leaving from the system? So that involves an unknown heat or work interaction. We need to assume the direction of heat and work interactions. So in such cases, it is a common practice to use the classical thermodynamics. So in the earlier class, that is in basic concepts, we have covered the classical thermodynamics and statistical thermodynamics. So classical thermodynamics is applied with respect to the environment, that is a standard reference frame with respect to standard reference frame, whereas the microscopic studies are going to be applied uh, for the high altitude applications. That is large number of data is required for the statistical thermodynamics. So the thermodynamics is going to cover only the classical thermodynamics and the sign convention and to assume heat to be transferred to the system in the amount Q and work to be done by the system, that is work output in the amount of W, and then to solve the problem. So this is the energy balance equation. What is the heat? It is what is the heat entering, that is Q in, net amount of heat entering Q in, minus what is the net amount of work output getting is equal to, that is this is nothing but delta E of the system, delta E of the system. So this is the energy balance equation, energy balance equation for a closed system, energy balance equation for a closed system. Now the time has come to apply the first law of a thermodynamic relation, that is Q is equal to delta U plus W for various process, for various process. So how you are going to apply that first law of thermodynamics for the various process? So this is the constant pressure process or isobaric process. So when you represent the general relation, that is PV to the power of n is equal to constant, in that one, when n is equal to 0, it is the constant pressure process or isobaric process. So the example for this particular case is nothing but like this one, a gas container. So some gas is stored in a container with a piston, and this piston which is free to slide up and down. If the gas gets expanded, the piston is going to move up. If the gas gets compressed, the piston is going to move down. So a gas in a container, sealed container with a piston that is free to slide up and down. The another example you can also consider that the boiling of water to steam. Say if you take the steam boiler, in a steam boiler, the water will be converted to the steam, or the freezing of the water to the ice. So in the process, sometimes the gas is going to expand or it is going to contract to maintain the pressure as a constant, and hence the net amount of work is done by the system or done on the system, right? So now you have to apply here, that is Q is equal to delta U plus W. Why delta U plus W? This is the stationary system. This is the non-flow process, stationary. So this is the stationary system, non-flow process. Now, what is the work? That is for a non-flow process. So the work is nothing but equal to PdV. The work is nothing but